Hello and welcome to video Fluids.1 about phases of matter, density, and pressure. This unit is a short unit about fluids. We're going to start with a bit of a review of some concepts that are important to understanding how fluids work, and then we will do a couple of examples to make sure you know what you're talking about in solving problems. The phases of matter, I'm assuming you all know it, but remember that a solid has a definite shape and size, a liquid has fixed volume but can be any shape, a gas can be any shape, and also can be easily compressed. Also remember that when we're talking about fluids, we are actually talking about liquids and gases because they both flow, they are both called fluids. There are two other phases of matter that we don't typically think about or come across in our everyday life, but worthy of mentioning here. The first one is plasma. A plasma is essentially a gas where the electrons have been stripped off because of the temperatures that it's at. And then the other one is sort of the opposite end of the spectrum, the Bose-Einstein condensate. A Bose-Einstein condensate is when separate atoms or subatomic particles get so cold that they clump together and start to act as if they were a single atom. So plasma and Bose-Einstein condensates sort of are at opposite ends of the temperature spectrum. From here, let's take a look at density. And again, I'm pretty sure that you have heard of density before. Remember that density, rho, is the mass per unit volume of an object. The units for density are typically kilograms per cubic meter. Sometimes the density is given in grams per cubic meter. When it is given in grams per cubic meter, make sure that you do in fact change it to kilograms per cubic meter. And remember, when you go from grams per cubic centimeter to kilograms per cubic meter, you want to make sure that you multiply by 1,000. If we take a look at this chart here of the density of some common substances that we're going to be talking about, first if we take a look at water. Water at 4 degrees Celsius is listed here as 1.000 times 10 to the third kilograms per cubic meter. We often think about it as just being 1 gram per cubic centimeter. Now, the reason why it says at 4 degrees Celsius is because remember that water has its own special properties with the shape of the atom, so that when the temperature gets below 4 degrees, it actually expands and the density decreases some. If we also take a look here at gold, for example, gold has an extremely high density, 19.3 times 10 to the third kilograms per cubic meter. We often think of lead as being really heavy, but lead is only 11 times 10 to the third. And then we have our woods, which are less than 1 times 10 to the third, and bone is around between 1.7 and 2. Density is important to think about when you are trying to look at which substances will float or sink in fluids. It is also important to look at when we are looking at how much pressure is around in a fluid or on a fluid. Okay, so let's take a look at pressure. Pressure is defined as force per unit area. It is a scalar, so it does not matter the direction that we're looking at. The units of pressure in the SI system are pascals. A pascal is 1 Newton per square meter because remember force is in newtons, area is in square meters. A few things that are quite interesting about pressure and things that you need to keep in mind is that pressure is the same in every direction in a fluid at a given depth. So if we have this cube here in the center of our liquid, there's an equal amount of pressure being applied to it in all directions from the liquid. If this were not the case, then the fluid would flow. It would be moving, and it would be moving this object around. Another thing that's important is if you're looking at the container and you want to know how much pressure the fluid is putting on the container, then you have to look at the force that is being applied perpendicularly to the wall of the container because pressure is perpendicular to the walls. Also, for a fluid at rest, there is no component of force parallel to any solid surface, because once again, if this parallel force existed, then the fluid would begin to flow. So pressure is perpendicular and it is equal in all directions within the fluid. This table here, table 10.2, is showing you conversion factors between different units of pressure. There are tons of different ways of measuring pressure depending on what the situation is. We will not use all of these different ways. We will typically stick to pascals or atmospheres, but in other aspects of, we'll also be looking at centimeters of mercury. But in other aspects of life, you may see these units given. Pressure at a depth h below the surface of the liquid is due to the weight of the liquid above it. So pressure is force per area, and force is due to the weight of the object, so we can change force to being mg, but then remember that density is mass per volume. So mass is density times volume. So we can change the numerator here to rho Vg over A, but then remember that really volume is the base area times the height, so we can convert that to an AHG. The A's cancel, and the equation for pressure that we typically use, other than F equals ma, is actually that pressure is rho GH, where h is the height of the fluid. This relationship is only valid for liquids whose density does not change with depth. Water, for example, density doesn't change per depth because it's barely compressible at all. We can also use this to find the difference in pressures at different depths. Say the height here, rather than being h, is h1, and we're interested in seeing how much more pressure there is on the cube if it is lower down, say down here to h2. Then the delta pressure, the change in pressure, is going to be pressure at depth 2 minus the pressure at depth 1, which we know then is rho g h2 minus rho g h1, which, as we said, this only works if the densities don't change with height. So the change in pressure is really rho g delta h. So essentially, as long as the density of a fluid doesn't change with depth, the pressure is proportional to the depth of the liquid. These are things to keep in mind once we start looking at particular situations of different depths of liquids with things in them. For example, when we look at a dam, dams hold water back on one side, so the back side of this dam would have a lake reservoir there, and the pressure increases with depth. So when we build a dam, rather than building the front face of the dam to be perfectly straight up and down vertical, we need to make the bottom of the dam extend outwards and be thicker, so that the more pressure we have down the bottom, the thicker you have of cement to push up against the water. It does not matter how large the lake is that is formed on the upstream side of the dam. It's only the depth that matters. So the thickness at the bottom needs to be the same, whether it's holding back a small body of water or a large body of water, if they are the same depth. Because this distance, horizontal distance here, it does not come into play in the pressure equation of rho GH. It's only the height that's important. All right, let's take a look at some examples. Let's go back for a minute to density. What is the approximate mass of air in a living room? 4.8 meters by 3.8 meters by 2.8 meters. Well, remember that density is mass per volume. The density of air, if we go back and take a look at our chart again for a minute, we find out that the density of air is 1.29 kilograms per cubic meter. The volume is 4.8 times 3.8 times 2.8, which is 51.072 cubic meters. So rearranging that equation, mass then is rho v 1.29 times 51.072, which is 65.9 kilograms. So the mass in this living room of air is 65.9 kilograms. So why don't we feel all of that squishing down? I mean, why doesn't it feel like we've got almost 66 kilograms squishing down on us? Because remember, the pressure is what we would feel, and the pressure is not just from the top of us, the pressure is being applied to us in all directions. So it doesn't feel anywhere near like 65 kilograms would. Here's another one. The 2 feet of a 65 kilogram person cover an area of 550 square centimeters. Determine the pressure exerted by the 2 feet on the ground. All right, well, 2 feet on the ground, that means that the force being applied is going to be due to the weight of the person. And we know that the mass is 65. We know that the area is 550 square centimeters. We need to change that square centimeters to square meters. And centimeters squared to meters squared means we need to divide. So 550 square centimeters becomes 0.055 square meters. Pressure is the force per area, which remember is mg over A. So 65 times 9.8 over 0.055. So the pressure from the 65 kilogram person is 11.6 times 10 to the third newtons per square meter. What if this person decides to stand on only 1 foot instead? Well, the area then gets cut in half. So the pressure will become twice the original pressure. So rather than the pressure being 11.6 times 10 to the third, it will be 23.2 times 10 to the third newtons per square meter. Okay, so now let's change from direct pressure and direct density equations to look at one with fluids involved. The surface of the water in a storage tank is 30 meters above a water faucet in a kitchen of a house. Calculate the difference in water pressure between the faucet and the surface of the water in the tank. So you can see that the tank's not filled all the way, but from the top it's at 30 meters. All right, density of water is, as we said before, 1.0 times 10 to the third kilograms per cubic meter. The delta P, the change in pressure of what we're looking for, is then going to be rho G delta H. The fact that the pipe bends here, and in these two places does not matter because there's no change in height at that point. And in fact, the point that it goes lower is not important either because we just want to know what the pressure difference is in this between this top and the faucet. So delta P then is equal to 1.0 times 10 to the third times 9.8 times 30, which is equal to 2.9 times 10 to the fifth newtons per square meter. Notice that the size of the pipe or the storage tank also do not come into play in this equation or in this problem. Just the height is important. All right, one last one. A dam holds back a lake that is 85 meters deep at the edge of the dam. If the lake is 20 kilometers long, I forgot a word. How much pressure would the bottom of the dam need to be able to withstand? So we have a long lake, we have a dam, 20 kilometers long, 85 meters deep. How much pressure? Pressure we know, again, is rho GH, so the 20 kilometers is not actually important. So 1.0 times 10 to the third times 9.8 times 85 means that the bottom of this dam needs to be able to withstand about 8.3 times 10 to the fifth newtons per square meter. That's an awful lot of pressure. How much of a pressure difference would there be if the lake was only 10 kilometers long? And therefore, how would the thickness of the bottom of the dam need to differ? This is not really a calculation. This is more of a think about problem. If the lake were only 10 kilometers long instead, is anything changing in our P equals rho GH equation? Well, no, because we haven't changed the depth. So because the depth of the lake is still the same, there is no pressure difference, and their thickness at the bottom of the dam would still need to be the same, whether your lake is 20 kilometers long or 10 kilometers long. This has given you a sample of most of the different types of pressure and density problems you're going to have. So now you can go ahead and get to work on your assignment. Bye for now.